Hello and welcome back. Over the next few videos we'll be discussing circuits. Now it turns out that most circuits can be categorized into one of two types. There are circuits that are powered by a constant voltage, and these are referred to as direct current or DC circuits. Examples of DC circuits would be basically anything that's powered by a battery, like a flashlight for example, as well as anything that uses logic circuits like a computer. The other major category of circuits are circuits that are powered by alternating voltages. And the reason these types of circuits are so common is that the voltage that is supplied by the sockets in the walls is actually an alternating voltage. So for example, most of the things that you plug into a wall that don't use an AC to DC adapter are using alternating voltages. So things like a blow dryer, vacuum cleaner, toaster, these are all AC circuits. And it turns out that analyzing AC circuits is much more complicated than analyzing DC circuits. And the main reason for this is that the voltage drop across different circuit elements in an AC circuit tends to lag the voltage that's supplied by the voltage source. So this can make things very complicated, and the typical way that we deal with this is that we analyze AC circuits using Fourier techniques and complex exponentials. And because the mathematics involved in analyzing AC circuits is so complicated, we're mostly going to stick to DC circuits in this class. The only other category of circuits that I can think of that's not on this slide are circuits that deal with signals. So for example, the voltage that's generated by a microphone or the voltage that you pick up from an antenna. One little thing that I want to mention about these types of voltages is that it turns out that you can analyze any voltage by treating it as a sum of alternating voltages and a DC voltage. So if you understand how to handle alternating voltages and DC voltages, it turns out that you can actually use that to analyze any voltage signal. So this is a very powerful technique to break things up into these two categories. Now, as I mentioned in the previous slide, most DC circuits are powered by batteries. And if you take a battery and you connect the two ends by a wire, the battery will create a voltage difference between the two ends of this wire, and that will in turn create an electric field, which will push the electrons from the negative end of the battery over towards the positive end of the battery. Now, you may recall in a previous video, I said that when a conductor is placed inside an electric field, the electrons inside the conductor will move around to try to cancel out the external electric field. Now, the interesting thing about a battery is that even as electrons move from the negative end of the battery over towards the positive end of the battery, the voltage difference between the two ends doesn't change. And the reason is that as these electrons go into the positive end of the battery, a chemical reaction occurs within the battery which basically gets rid of that charge. So even as charge moves from one end of the battery to the other end, the voltage difference remains the same. Now, for historical reasons, the voltage that powers a circuit is sometimes referred to as an electromotive force, or an EMF. And an important thing to understand about the electromotive force is that that's not actually a force, it's just a misnomer. And we can see this because the EMF is a voltage, and we know that the voltage is defined as being the change in the potential energy that occurs when you add a charge to a system divided by the charge that you've added. So we can see that the EMF is going to have units of joules per coulomb, and that's not the same thing as the unit of force, which is newtons. When working through problems that involve circuits, we'll frequently draw circuit diagrams to illustrate how the different components of the circuit are connected together. The symbol we use to denote a voltage source consists of two parallel lines of different lengths, like I have shown here. Whenever we draw a voltage source like this, the longer line represents the positive end of the voltage source, and the shorter line represents the negative end of the voltage source. If you have a hard time remembering this, just think that the longer line has a larger voltage, right? So the larger line is a larger voltage, so that's the positive end. The smaller line has a smaller voltage, so that's the negative end of the battery. Now, as I mentioned before, if you connect the two ends of a battery together with a wire, charge will move from one end of the battery to the other end of the battery. And one of the things we would like to be able to describe is the rate that charge moves through this wire. And to do this, we create another quantity called the current. and the current is defined as the rate that charge moves through a wire, or in other words, it's the charge that moves through a wire during a time delta t divided by the time delta t. As we can see by applying dimensional analysis, the units of current are going to be coulombs per second, which is denoted as an amp, or an ampere. And we denote the current with the capital letter I. By convention, we say that current points in the same direction that the positive charge is moving. So for example, in this picture, I have these positively charged particles that are moving to the right, so the current points to the right. However, in most materials, it is the electrons that actually move in response to an external field. And because the electrons are negatively charged, the electrons move in the opposite direction as the current. So for example, in a wire, these electrons might be moving to the left, so the current points to the right. The charged particles that move inside a material and give rise to the current are called charge carriers. Because current has direction, current is actually a vector. However, current is kind of an interesting vector because the current can only flow along the length of the wire, and this means that current can only have two different directions, which means that current is effectively a one-dimensional vector. And like all one-dimensional vectors, we can denote the direction of the current with a plus or a minus sign. So typically when we're working through circuit problems, we'll usually draw arrows along the different lengths of the wire, and that'll denote the positive direction of current flow. And if the current flows in the opposite direction, then we'll denote this with a negative current. In most circuits, we'll be able to guess the direction that the current flows. As we've mentioned before, positive charge always moves from places of a higher voltage to places where the voltage is lower. For example, in this picture down here, I have a positive charge that's placed between two oppositely charged plates. The positively charged plate has a positive voltage, and the negatively charged plate has a negative voltage. Because the positive charge is repelled from the positive plate and is attracted towards the negative plate, the positive charge will move from the plate that has a higher voltage towards the plate that has a lower voltage. The same thing is true inside a circuit. This means that the current will always flow from the positive end of the battery towards the negative end of the battery. So in this circuit here, the current is going to flow around counterclockwise like this. So let's look at an example. This example says a 12-volt battery is connected to a battery charger for 5 hours. The charger carries charge from the low voltage end of the battery back to the high voltage end of the battery. The charger moves charge at a rate of 6 amps, and the voltage across the battery remains 12 volts during this time. Part A asks us to determine the amount of charge that's transferred to the battery, and Part B asks us to determine the energy that's transferred to the battery. So Part A is relatively straightforward. Current is equal to the rate the charge moves from one end of the battery to the other. So if we rearrange this, we can see that the charge that moves through the wire is going to be equal to the current times delta T. So this is going to be 6 amps, and we have to be a little bit careful here because delta T needs to be in units of seconds. So this is 5 hours times 3600 seconds per hour. And if we plug this into a calculator, we'll see that the total charge that's transferred from one end of the battery to the other is 1.08 times 10 to the 5 coulombs. Now the second part of the question asks us to determine the amount of energy that's transferred to the battery. So what we need to do now is we need to relate the change in the energy to the charge and the change in the voltage. Remember that the change in the potential energy is going to be equal to the charge that moves through a voltage, delta V, times the voltage difference, delta V. So this is going to equal 1.08 times 10 to the 5th coulombs times 12 volts. And if we plug this into a calculator, we can see that the energy that was given to the battery is 1.3 times 10 to the 6 joules. So at this point, I think I'd like to end this video, and in the next video, we'll discuss something called Ohm's law.